Hello everyone and welcome back to our series about teaching maths in the FET phase. Let's first take a look at our video, which goes deeper into the topic of teaching analytical geometry. The circle is something we're likely to experience on a daily basis. Think about it. When we get into a car, we're surrounded by several examples of the circle. The steering wheel, the wheels on the car, the knobs on the radio, etc. A great leap in human civilization came about with the invention of the wheel. The circle keeps cropping up in science and especially physics, albeit often in a subtle and disguised way. The circle also forms an important section of analytical geometry. A large amount of time is spent studying the circle with its center at the origin. In this video though, we will investigate the equation of a circle whose center does not lie on the origin. At Residential Secondary in Sebokeng, the teacher, Mrs. Weslina Gaula, is preparing a lesson on circles.
Can you tell me about the everyday's life, where you come across a circle?
A steering wheel is a circle.
The buttons of the shed are the circles, ma'am.
I have a sharpener here. It's a circle.
The outcomes of the lesson for the learners are to demonstrate the relation between the circle at the origin and the circle not at the origin in terms of the distance formula, use exploratory techniques to derive a formula for the circle not at the origin, find the radius and/or the center of the circle not at the origin.
The pupils had to find the equation of the circle using the knowledge that they have of a distance formula and also the knowledge of the equation of a circle having the center as the origin.
The lesson begins with a review of the properties of a circle.
What is it that you know about the circle?
The line that is drawn from the center of the circle to the circumference is called the radius. And then we have the diameter, which is the line that cuts the circle into two equal parts.
Is there any relationship between the diameter and the radii?
Yes, diameter is the 2 multiplied by radii.
Apart from the radii and the diameter, what is it that you know?
The circumference is the outer part of the circle.
We also know that all the radii on the circle are all equal.
In this activity, learners require a compass, graph paper, and a ruler.
On a Cartesian plane, just try to draw a circle, and the center has to be the origin. We want all of you to have the same circle.
All learners draw a circle with a radius of 5 units.
You know exactly where to draw. We use that center of the circle as the origin to determine the radius of the circle. And to do that, we have to use the distance formula. We can also use Pythagoras method, but we wanted to emphasize the distance formula. On the circumference of the circle, put a point there. And afterwards, check for me through counting what will be the coordinates of that point.
This is my point, and my coordinate is -4 and 3.
The teacher explains how the coordinates are determined.
They've counted the blocks from 0 up until -4, and there they counted, they checked their y, and they had that point -4 is to 3. But now, what is it that you can tell us about the points that are around the circumference?
These points, we can use them when you calculate a distance from the origin point to the circumference.
Just tell us, how can that be done?
We can do that by using the distance formula.
Can you mention the distance formula?
D equals to the square root of x2 minus x1 all squared plus y2 minus y1 all squared.
Can you use that formula and find the radius?
The learners use the formula d squared is equal to the square of the difference between points x2 and x1 added to the square of the difference between y2 and y1. This means that d is equal to the square root of the square of the difference between points x2 and x1 added to the square of the difference between y2 and y1. A learner will now substitute these coordinates into this formula.
Okay, this point 4 being my x2, then it will be a -4 minus, okay, x1 will be 0,
Because the center of the circle is at the origin, the value of x1 and y1 is 0. After substituting, the radius is determined to be 5 units.
With that information, having the radius equal to 5 and the points that you are having, is it possible, and how are we going to determine the equation of the circle?
Learners know from previous lessons that the formula for the equation of a circle with its center at the origin is r squared is equal to x squared plus y squared.
They had to use the knowledge or the radius that has been calculated to determine the equation of that specific circle. In other words, the equation of the circle is equal to x squared plus y squared is equals to 25. Or we can say x squared plus y squared is equals to 5 to the power 2, or 5 squared.
In this activity, the teacher asks learners to look at what happens if the center of the same size circle is moved to another center point.
4 is to 5. All right?
The learners measure out these coordinates and draw the new circle.
Okay.
You have the center of the circle where you have point 4 is to 5. On the circumference, get another point. Just get the coordinates of that point.
A point is chosen and the coordinates determined.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And our point is 5 is there.
The next step is to determine the radius of the new circle using the coordinates.
Use a distance formula to determine the radius. Using those points, you are using how many points? This one and that one.
Learners use a distance formula to establish the radius.
When you use that point to calculate the radius, what is your radius?
Radius is 5.
What is the conclusion that you can draw here?
The two circles are equal because the radius are equal.
The teacher now leads her learners to move from their specific example to developing a general rule by replacing the coordinates on the circumference with two unknowns, x and y.
I have x is to y. Now, is it possible to use the center 4 is to 5 and point P where we have x and y to get the equation of the circle?
A learner uses the distance formula and substitutes the known coordinates.
Right? We have substituted, and this is what we came up with. What do you think it's this? What do you think it's this?
The equation of the circle.
With the center, what?
4 is to 5.
4 is to 5. Now we're going to change the center.
The teacher will now replace the last known coordinates, that is the center of the circle, with unknown coordinates and also an unknown radius.
I want to get somebody to determine the equation of this circle. A new circle with the center A is to B, with the point X is to Y.
Learners use the distance formula for the length of the radii to write an equation for the circle. He uses the endpoints of the radii, that is x, y on the circumference and a, b at the center.
Okay, let this be x2 and y2. Let that be x1 and also y1. Okay?
The teacher now rewrites the formula he has developed in its standard form using AB as x1, y1 and xy as x2, y2.
Minus a and all squared plus.
After substitution, the teacher comes up with the equation r squared equals square of x minus a plus square of y minus b.
In other words, any circle, it doesn't matter, even if you don't have the center as the origin, this can be used to determine the equation of the circle. This is a general formula for determining the equation of the circle.
So we see that finding the equation of the circle is merely an application of the distance formula, provided we know the coordinates of the center and the length of the radius.
And in the end, we've discovered that in general, the equation of the circle with the point anywhere will be equals to r squared is equals to x minus a all squared plus y minus b all squared.
Now that we've seen the video, it's time for us to welcome our guests for this session. We've got Maggie Verster, who's the webmaster of the Easy Maths community website, And we've got Catherine Hunter, independent maths consultant, maths education consultant. And we've got Taska Matlejwane, who's a principal at Pafokgang Secondary School in Rockville, Soweto. Thank you for joining us. The first question, let me start with you, Taska. Why was the activity of adjusting the circle formula of value to learners?
It's very important for the learners in the sense that learners shouldn't see a formula as something that which they need to memorize. It must be something which they generate themselves. They've got to create it, and they should know that those symbols can always be changed. The most important thing is how these things were created. And now if you change scenarios and generate a formula, the way they've done it on the video, I find it much more helpful for learners.
Okay. Catherine?
I think it was a very good exercise. I think what the possible outcome would be that the teacher would only do this once. And I think it's quite important for the teacher to do it repeatedly, the same exercise, for learners to be able to substitute into the formula a variety of points to really believe and consolidate their understanding of the link between the practical application that they've done in the classroom and the formula.
Okay. Maggie?
The learners like to hold on to formulas, but what happens if they get to exam where they are under a stressful situation and they forget the formula? Then they've got to revert back to their understanding of the content there. And if they actually can think back to a practical situation, they can figure out the formula from scratch for themselves. So it's a sort of a safety measure for them, and it also tests their understanding of the formula.
Okay. Maggie, in the video, the teacher asked the learners to think of examples of circles from everyday life. Why do you think she did that?
Well, we always have the learners asking us, why do we have to do math? What does it have to do with real life? Now, math is real life. There's wheels, circles. It actually just binds the real life to our mathematical knowledge. It is vitally important.
Catherine?
Although I think it's important exercise, I think in this particular example, it didn't come across with its full value. I think the teacher could have made more use of the fact that circles in real life, we're not just playing with circles on a graph paper or on a Cartesian plane, but linking it to real life situations. It's hard to look into real life and see something that is a meaningful example that would show learners, to be able to answer Maggie's question, show learners what the point is of asking that. But I think that at every point, teachers need to make it quite clear to learners that what they're doing inside the classroom is going to be for their use outside the classroom as well. So any links that can be made, I think, are of benefit.
Taska?
Yeah, I quite clearly agree with my colleagues here. As a notion of contextualizing mathematics, if you quote examples in real life, learners see the direct need for mathematics, and they see the direct need for why circles within the curriculum of mathematics. And they start to place value in whatever they are doing. And that, I think, brings a greater value to the lesson in terms of motivation.
Okay. Catherine, do you think the teacher could have made greater use of group work during the lesson?
I think the teacher did make quite good use of group work. She did draw on the learnings of the little groups and ask learners to come forward, for example, up to the board to substitute the points on the circle, the second circle, the circle that did not have the origin at its center, and show how they substituted their points into the formula and so on. I think maybe we haven't seen the whole class, of course, the whole lesson, but it would have been of value to substitute several points into that and show that no matter what point was being, the different groups were experimenting with, all did fulfill the formula. But I think in general she did. And of course the group work is so important just because the learners talk amongst themselves and are therefore able to clarify any questions amongst themselves in language that is meaningful to the learners, because sometimes the teachers are out of touch and talk in a too academic way or in some way that is not easily accessible to a wide variety of learners, and group work does serve that function.
Okay. Maggie?
Absolutely. I must say, from the little bit that we saw from the video, I sort of got the feeling that she didn't quite make as much use of group work as she could have. I actually think that the one big advantage of group work, rather than actually sending the learners up to the board to go and do it, is while the learner is doing it on the board, you lose the rest of your classroom. Whereas if you keep it confined to a group, they can explain it to one another, and they can clarify the concepts within the group, and they can internalize it on an individual basis. We know that peer pressure within little groups work wonders for knowledge. And actually learning in a little group is essential.
Tasker?
Yeah, I really agree with them, because a group, the value of group work, I think is inexhaustible. There are many values which can be attached to a group work. And like it or not, maybe the teacher couldn't have really exhausted the list. But what I think he should have also not left out is to give them varied type of assignments, pieces of work, not for them to work on one and the same thing. But at the end, when they display the work, it should all come up as the same formula.
Maggie, one of the key features of analytical geometry is the combining of algebra and geometry. Now, what challenges does this pose for teachers?
Well, I actually don't think it poses challenges. It is this golden magic tool that you can use between geometry and algebra. I actually find sometimes a learner is strong in geometry but does not like algebra, whereas analytical geometry provides that bridge between the two. With geometry, you are working with shapes and proofs. Learners find proofs quite hard, and therefore they sort of tend to learn it off by heart, which of course is not the best way to internalize it. Whereas algebra, you work with numbers and variables, and analytical geometry brings these two areas together, and it makes it real for them. So if they can work with numbers and they can implement it in a geometrical shape, it just makes so much more sense to them.
Catherine, you'd agree?
Absolutely, I would agree. I think part of the challenge facing teachers is that throughout the rest of the years of learning that the learners have been through, formal learning, they don't often have sufficient practice in being able to interpret diagrams and to being able to appropriately use accurate diagrams versus rough sketches. So I think it's an important thing that the teachers always give learners ample opportunity to use sketches, to interpret them, to manipulate them, to lay a solid foundation for teachers at FET level to be able to build on.
Okay, Tasker, can you add to that?
Yeah, I find it being an advantage of combining algebra and geometry, because it seals off everything. A learner who meets something even in synthetic geometry, when it comes to analytic, he starts to pick it up now in a different way, and that makes knowledge more wholesome.
Okay. Are there any other issues you'd like to raise?
The one thing that I just want to clarify from the video is the learners referred to a point as 4:5. Is that an accepted terminology to use for a coordinate point, 4:5?
I've seen it in quite a variety of classrooms, but I think it's confusing, and I think it should be corrected. I think the teachers themselves should correctly refer to the coordinates of the point.
How do you correct something like that, Tasker?
It should be A and B as a coordinate. Coordinate A and B, meaning that you call the numbers within that point. But if you say A is to B, you talk of ratio now.
That's the problem.
And I think it's misleading maybe some of the learners. So the question of concepts, I think, should also be looked into very, very seriously.
Doesn't that maybe arise from a matter of language in the classroom?
Yes, there are quite a few sort of language peculiarities that we see across our classrooms, and it'd be interesting to know where they come from. But I think it is important for teachers to refer to the textbooks, refer to their training, check out with colleagues and use the language correctly, because the learners pick it up and in fact misuse it. I mean, as Tasker says, that saying 1:2 is the way in which we speak about ratio, and we don't want them to think in this particular case it's to do with ratios.
We're dealing with ratios. Maggie, it's common for learners to confuse the center of a circle with the origin of the circle. How can those misconceptions, well, it obviously leads to misconceptions, how can those be dealt with?
Well, there is actually quite a big difference between the origin of a circle, the origin and the center of the circle. The origin is terminology that's used for a Cartesian plane where the x-axis cut the y-axis. That's the origin. So here we go back to terminology which the learners learn in grade 9, I think. And we just need to reinforce that that's a specific term for the point 0, 0. Whereas the center of the circle can be anywhere. It can be traditionally at the point 0, 0, but it can be anywhere else on the Cartesian plane as well.
And Catherine, obviously important to raise that with your learners as you go along, would you think?
I think that's a very good example of why it's important for, at the start of any new topic, for a teacher to consolidate the learning that the learners already have, and to check that in fact all the learners are on the same wavelength. So for example, she could compile a list of questions that she asks the small groups to discuss that in fact reflects knowledge that maybe would be built in years before the current one, but at the same time just lay the foundation so that everybody is using the terminology correctly and everybody is referring to the same thing when they use some of those words.
Anything else you'd like to add, Meg?
Yes, there is one problem area that I find that the learners have when it comes to circles, and that is it's all very well when you're using the distance formula to get the equation of the circle, but as soon as you multiply it out, you have got an equation that looks very foreign to them. And then, of course, we know to get it back into the distance formula kind of equation, you've got to complete you've got to complete the square, which they find quite hard. And to recognize that equation is a problem for them.
Catherine, the use of a compass could be a problem when dealing with circles.
I was very impressed that they were using compasses because, again, as Tosca mentioned, that the equipment is so important in these classes, and often learners have not been able to experiment and design patterns and so on using a compass, which means they don't develop an intuitive sense about the characteristics of a circle, which is fundamental to this particular exercise. So I think that was very encouraging to see it there, and certainly as that is one primary piece of equipment that is needed to lay the foundation solidly for analytical geometry.
That's all we've got time for. Thank you for joining us as our guests, Tosca, Catherine and Maggie. And thank you at home for joining us. Do keep your eyes peeled for Module 12 coming up in this series. Thank you for watching. Goodbye.